Okay, before proceeding our lecture, I have one notice. So here we have now 8 teams confirmed. So this about 8 teams from team 1 to team 8, they are having more than 3 members. So you can group like this for team 1 through team 8. But for the members of team 9 to team 12, because you are having less than 3 members, so we are encourage you to merge your teams. Okay, so out of these 4 teams having just 2 members, I encourage them to make 2 teams having 4 members. So after this class, at least one of this team, one member of this team, have to may remain here and discuss the merging things with me. Okay. So after this class, please remain and discuss the merging things with me. Okay. So we will eventually have like 10 groups. Okay. For the final project. Okay. And another thing is here we announce the final term project, and in the above you can see by the 27th of May you have to submit video recorded video for the final presentation, and we will watch the video together and have the Q&A session in subsequent 2 lectures. Okay. But previously I mentioned that the video had to be in 10 minutes, but I changed it to 7 minutes now. So it's denoted as the pink color here, right? So you have to record 7-minute video by 27th of May. And the video had to be recorded in English. Okay. And you may include that video can include some proposed idea and data collection and usage plan and reference paper list and data collection examples. Or if you use the publicly available data set, then you have to list those data set. And also maybe you can present some intermediate result. Okay. So the video presentation submission, that is actually 2 weeks remained. Okay, so please start preparing it. And because the time is quite limited, I'm expecting that you will get only the initial result for this presentation. Okay, so by this presentation you can share some initial result, and by the June 19th you can submit the final result. Okay. And the thing is, because the training images are only around 500 images, we are giving you only 500 training images, and the testing images are around 9,000 images. So, I mean, if you use the real-time object detection pipeline, the training will not take much. Okay? So, I mean, so in that sense, I think 2 weeks are, I mean, the maybe somehow enough time, maybe for training. But anyways, you can only share the initial results by then. Okay. Okay. And another thing is the programming assignment 2 is deadline is 15th of June. So don't forget this. Okay. And we will have also this is remaining schedule. So today is here, and this is holiday, so we don't have class. This Wednesday we don't have class, and next week we will see another lecture for. We will see some application of vision language models in computer vision domain. So this would be the last lecture. And here we will take the quiz 2, okay? And you have to also submit the final presentation video by this date. And this week, we will have the final presentation. So in the lecture, we will proceed our final presentation Q&A session, actually. And this is the second Q&A, okay? And here we will have no class. And this would be the final exam period. But we don't have any final exam this week, okay? And here, PA2 deadline. And this is the final term project deadline, okay? So this is the remaining schedule, okay? Are you understanding this? Okay. So next and today, that would be the last lecture, and we will have quiz 2 here. 그래요? 이렇게 됐네. 이게 슬라이드가 넘어가서 보이네. 하필 그림이. I will re-explain. So here, this is today, and here there will be no class. And here, next week, we will learn about vision language models. And here we will take quiz 2, okay? And you have to also submit the final presentation video, 7-minute video by this date. And here we will have Q&A session 1, and we will have Q&A session 2, okay? And here, this day, we will have no class, okay? And this week is for final exam, so, but we will not take any final exam, okay? And this day is for PA2 deadline. And this is the date for final term project, okay? You have to submit all the report and all the code and data by this date. Okay. Are you now understand this schedule? Okay. So this would be our last lecture, and this is quiz 2, and have the final presentation. Then our class will be maybe ended. You don't have to anymore attend the class, but you have to 2 deadlines for final term project and also the programming assignment too, okay? This is the remaining schedule, okay? Okay. Pseudo labels. So last week, we learned about the knowledge distillation, and also we also learned about the pseudo labeling, okay? Basically, what pseudo labeling means, this is somehow meaning the fake things. Pseudo is meaning fake. So we don't have labels which is made by humans, but we will regard some labels estimated by the teacher network as the real label, but we will name it as the pseudo label to train another network, okay, to exploit both the labeled and also the unlabeled data. That's the pseudo labeling. Okay, so this is the concept. So we first train the teacher network, and with the labeled data set, and we somehow want to train the student network using some unlabeled data. Okay, so this can be stated like this. Okay, and this is the interesting result published in CVPR 20. So if we train the teacher network using labeled data and infer some pseudo labels for unlabeled data and using the similar architecture to the teacher network, we will randomly initialize, we will regard it as the student network and randomly initialize it. And if we train that network using the both labeled data and also the unlabeled data, but the data injected with some noise, this kind of noise, then the paper is saying that we can get the new, we can get the trained student network, but we can regard that as the new teacher network and iterate this process again and again. Then we can get a student network whose performance is actually better than the teacher network. So this is saying the same process. So learn teacher network on the using the labeled images. So this is the loss function for that. And and this is the process for obtaining the pseudo labels for unlabeled images and learn the similar architecture to the teacher network using both the labeled images and unlabeled images with noise added, okay? And using both, we will train the student network. This is the loss function for sorry, this is maybe the labeled data, and this is loss function for maybe unlabeled data. Okay, so there are n labeled data, and somehow they are saying there are m unlabeled images. Okay, so this is the loss function for unlabeled using pseudo labels, but this is for training the student network using the n labeled data. Then we will iterate this process by regarding the trained student network as the new teacher network. And by doing that, the conclusion is the noise student performs better than the original teacher network for all the cases, okay? So this red graph is the noised student and blue graph is the state-of-the-art image classifier. Okay, so this is the number of parameters and this is the accuracy. So given same architecture, the authors are saying via this process, additionally exploiting the unlabeled data when training the student network becomes even better than the teacher network. And this is the example of the noise added. So this is the list of the random noise added when training the student network. So identity transformation, contrastive, we can change the contrastive, the color distribution, and several other noises are randomly augmented into the training process of the student network. So we can also adjust some hyperparameters when applying the transformation. Okay, and this is the examples of the obtained samples when training the student network. Okay, this is unlabeled, actually the unlabeled images transformed via the random noise. Okay. So pseudo labeling, that's the good way to augment the augment the data using the unlabeled images. But thing is, it has some. Sometimes it could improve the performance, but sometimes if the pre-trained teacher model is not accurate enough, then the pseudo labels become inaccurate, and it can negatively affect the training process of the student, and it can spoil actually the training of the student. So to relieve that thing, this kind of meta pseudo labels, that kind of schemes are also proposed in CVPR 21. What they does is previously in pseudo labeling, there is only one way. Okay, so teacher model is used to get the pseudo labels. This head YU is the pseudo label for unlabeled images XU, and student network will exploit these the images input and the ground truth as the pseudo labels as the ground truth. The student can be trained, but the pseudo labels itself could be inaccurate. So there's another route that can that the teacher model can be affected by the student network. Okay, so that scheme is actually called as pseudo meta labels. So here, this part is same as before. So by minimizing the loss function for unlabeled images, the student network's parameter sector S is obtained. So this is done for training the student network, but this part is also added in meta pseudo label schemes. So what this part is saying is they will use the labeled data to choose the teacher parameters. So this is the teacher's parameter, and using the student parameters, given student parameters, we will select the best teacher's model that minimize the loss functions on the labeled data. So this part is newly added, and somehow the teacher, when training the teacher, it also gives some feedback from the student model. Okay, so somehow it can improve. The teacher model can be also improved by the current parameters of the student. And so the second term, this term can be updated, optimized by the standard gradient descent algorithm. Okay, so student network's parameter sector S is getting the gradient from the unlabeled data and multiplied by some learning rate. It is updated. So this is the standard gradient descent. And also the teacher network, their parameters are also affected by the updated student network's parameters. And sector T is actually also updated. That's the newly introduced scheme in meta pseudo labels. And what they does is they also use the standard gradient descent for updating the teacher's model. Okay, so this is the loss function introduced in previous slide. This is the loss function, same loss function. And by getting some gradient for this loss function, the teacher model's parameters are also updated. Okay, and also the student network, it is updated in the same way as before, using the standard gradient descent. It is updated. Okay, so this is the meta pseudo labels, and using the image classification data set, they are saying it is, I mean, even better than, sometimes even better than the supervised learning. So this is the performance of the supervised learning, but sometimes it is less than. For example, this case, it is less than the fully supervised method, but sometimes they are better than the fully supervised method. Okay, especially ImageNet, it has a lot of data samples. Okay, so the data samples, they are somehow large enough to understand the original training data set distribution, but especially for the small scale data, sometimes the fully supervised method, it cannot properly make the model to understand the distribution of the original training data. Okay, so in that case, the performance is better than fully supervised method. Okay, so this is another example, another toy example for this fact. So this is the supervised learned models decision boundary. So actually these lines and color are denoting the decision boundary of the model. So there are green and red regions, and these regions are indicating the model's decision boundary. Okay, so when samples are here, the model will regard this as the green sample. And when samples are here, then the model will regard this as the red class. Okay. And actually this blue star, those are samples, I mean, the real samples sampled from the training data distribution. Okay. So I mean, using these discrete samples, the model will be trained. Using these blue stars as the training data, the models are trained in the fully supervised way. Then the model's decision boundary could be wrong. Okay, actually, the data set, the true data set is these moon-shaped data. I mean, this is the true training data distribution. So ideally, the model have to understand the distribution of this training data and make the decision boundary like this actually. So for samples in these regions are all have to be classified as red. The decision bound the samples located in this region have to be classified as green. But using only limited samples, the blue samples, if the model is fully trained in the fully supervised way using this kind of limited data set, then model becomes not very ideal. So their decision boundary is not understanding that the training data distribution is actually the moon-shaped. This is the moon-shaped data. But I mean, this is the true distribution, but the training samples actually is limited. So when the model is trained in the fully supervised way, the model cannot understand actually the true data distribution. That's the limitation of the fully supervised learning. And because of that, when this model, this teacher model is exploited as the teacher model to make the pseudo labels, the student model trained by these pseudo labels are also suffer from correctly figure out this moon-shaped data distribution. So the decision boundaries are somehow wrong. Okay, but using these meta pseudo labels, the paper authors are insisting that this model, they are correctly detecting the data distribution, training data distribution. So somehow their decision boundaries are following the moon shapes. Okay. So this is the merit of meta-pseudo labels. Okay. So, but in practice, you will, the easiest way to use these pseudo labels is just involving good teacher. If you are, given some sufficient data, trained data, and can have the sufficiently good pre-trained teacher, then maybe just using the pseudo labeling skills might be enough. Okay. And next theme is the transfer learning. Okay. So this is also similar to pseudo labels or KD, but compared to the knowledge distillation, it is originally used for making the smaller models that solve the same task with the teacher model. Okay, but the transfer learning is having the different goals to achieve. In the transfer learning, its aim is to train the new network which does different tasks, different but similar to the original task. Okay, so their aim is solving. In the transfer learning, the teacher model is already having some knowledge gained by the large-scale training, and the aim of the transfer learning is to apply it to somehow different but similar or related task. Okay? So the transfer learning is first conducted for this kind of task. So we train the network using the ImageNet pre-trained network like the AlexNet or the VGG network. So this is the large network trained by the large data set. And transfer learning happens but when we want to fine-tune this large network pre-trained by the large data set towards the different tasks, different or smaller or the similar tasks that classifies the cat or dog, okay, or some other tasks like depth estimation, or somehow different tasks like 3D pose estimation, like that. So using this kind of already pre-trained network to other similar related tasks, this technique is called as the transfer learning. Okay, but the KD, the teacher and student are normally sharing the same task, but the objective is getting the smaller network or improved network for the same task. That was the aim of the knowledge distillation. Okay. So this is the pipeline for getting another image classifier using the pre-trained ImageNet pre-trained network. So given ImageNet, we first train the randomly initialized deep learning network. And it was, because the ImageNet is having 1,000 classes, the network is trained to classify 1,000 classes. And then somehow we remove the last part of the network and replace this to fit to our own new task. And then randomly initialize the last part. And normally we freeze some of the layers in the early layers, we freeze and fine tune the, normally the last layers or some of the later layers, we fine tune the later layers using the new data set. That's the called as the training transfer learning scheme. Okay. So I'm assuming that most of you are familiar with this transfer learning. Okay. So this is the thing happened for the ImageNet pre-trained network. So this might be AlexNet, okay, having multiple CNN network. And later part, we have the fully connected layers. And we first train this network using large scale data sets such as the ImageNet. And then we replace the last layer and we initialize this later layer to fit to our own task. So the new task have the C class, this dimension have to be C, okay? And we reinitialize this part and freeze the early layers and train the later layers only using the small data set, okay? This is the transfer learning. And this is the easy implementation of the transfer learning. So using this, the famous networks are already provided in the PyTorch library. So using that, we can easily initialize the AlexNet, which is one of the famous deep learning architecture. And by doing this, you can initialize the AlexNet. And if you print out it, then you can see this kind of network architecture. So first part, it is composed of multiple convolutional layers. And then later part, those are constituted with the fully connected layers. Okay, this is the visualization of the AlexNet. And the thing you have to do is first freeze the earlier part, okay, and then replace the last layer to fit to our new task. So previously here, it has 1,000 classes because the ImageNet dataset, they are having 1,000 classes. So the last layer have to have 1,000 dimensional vector to output 1,000 dimensional probability, okay, for each semantic class. But here we replace the last layer having only 10 dimensional vector because our new task will have only 10 classes, okay? So the last layers are replaced and the other layers are freeze, okay? And this is the new visualization, okay? And then we can train this network for new small task, okay? That's the transfer learning. Okay, are you guys following this? Okay. And another thing I want to share is the self-supervised learning. This is also similar to pseudo labeling or the KD in the sense that it is not requiring any manually labeled data. Okay, so this is another method for using the unlabeled data. Okay. Okay. So the self-supervised learning, it means learning without the tagged data. So it is also the schemes for using the unlabeled data during the training. Okay. So, and also it could be applied to any forms of the data. So speech, image, and video, text, and so on. Okay. So this one of the representative self-supervised learning was done in the NLP, the natural language processing domain. Okay, so this is the transformer architecture we already learned. Okay, And actually, this was the scheme to learn the BERT network. Okay, so this was one of the precedent of the GPT network. So now we are using GPT-4, okay, and OpenAI, they are saying they will release the GPT-5 in near future. But before this, BRT was the state of the art for NLP tasks. And what they did was this. They apply actually the self-supervised learning on the text data to obtain this BRT, which is the large scale language model. So the transformer was trained by using two supervisory signals. Okay, the first is the masked language model, and the second was the next sentence prediction. So this term seems like difficult, but it is not that difficult. What they actually does is their data is having this form. So here in the sentence, they have mask tag, okay? So they on purpose delete some of the word here, originally here, okay? And what they do here is using the other words as the context, as the input, their task is to estimate this masked words, okay? So this is called as the masked language model. And the next sentence prediction was, actually there are two sentences here, right? This is the first sentence and this is the second. This is the first and this is the second. And this is the first and this is the second, okay? And this is the label saying that if the second sentence is actually the next sentence of the first sentence. So if it is correct, then the label is next. And if it is not the case, the labels is not next, okay? So these two sentences are not originally the sequential sentences, okay? So it is labeled as not next. But these two sentences are originally, in the sequence. So they are labeled as is next. So that thing is the next sentence prediction task, okay? So given this data, they first estimate the masked word. That's the first supervisory signal. And the next is to decide whether these two sentences are in sequence or not. That's the second supervisory signal. So using these two, the transformer, it is trained using large amount of this form of the data, text data. So that was the BERT network. And using this unsupervised, the self-supervised learning, they are using the transfer learning to fine-tune this large-scale language model to the downstream tasks. That's the concept of BERT. And actually, GPT, those are also same, okay? So this is the representative self-supervised learning, okay? So, the motivation for this self-supervised learning is we cannot label the large-scale data by human effort. It is quite effort-taking. So the motivation for this self-supervised learning is we can find some clues inherent in the data themselves, okay? So we can on purpose mask some of the words inside the data and can make the network to estimate them. or also we can make some sequential prediction task, I mean, inherent in the data themselves, and make the transformer to estimate it. Okay, that's the motivation for this. And this was done for natural language processing domain. And what people thought is how to apply similar concepts in computer vision domain. So this ICCB of 2015 paper, they are proposing some similar self-supervised learning method for the image domain. Okay, so for example, what they does is given this kind of data, image data, um, they don't have, let's assume they don't have any labels for this image, then there would be no way to train the deep learning architecture. But what they did was they on purpose make some patches on these images, and they are involving this kind of AlexNet style deep learning architecture. Okay, actually they are using just one, and I mean share this network twice for the training. Okay, and they can detach some of the patches and rescale it, and to input these patches to the deep learning architecture. And what they actually estimate is the location, I mean the relative location of the patch. Okay, so for example, if the patch is located here, I mean, if we input this center patch here, okay, and if we input the patches located in this area, then the output should be 1 because the index here is 1, okay? And for example, the patches located here is inputted, then we have to estimate maybe number 3, okay? So we can phrase this task as the classical classification task, okay? So the thing we have to estimate is the number 1 through number 8, okay? So using this kind of pipeline, we can actually train this network, okay, without any image labels, okay? So this is one example for self-supervised learning in image domain. Okay, so this is what is explained here. So context prediction. So predict the relative positions of the patch. Okay. So by doing this, maybe without any labels, the deep learning network will gain some knowledge of the relative positions of the patch. Okay. And maybe after training the network using this kind of self-supervision, we can fine-tune the trained network to the downstream tasks. Okay, so that's what can be achieved here. And the maybe 16, this is the published paper in ICCB 15. And here, ECCB 16, the similar self-supervised learning was proposed. So here, this is the image without any labels. So we extract the 9 patches from there. And this time, we don't merely estimate the relative positions, but we actually permutate the 9 patches extracted and actually estimate their permutation order. Okay, this is the scheme proposed in this ECCB 16, and they are saying they are better than the simple schemes. Okay, but the thing is, actually, there could be 9 factorial permutation if we are involving 9 patches. but it is somehow too much for training the network. So as far as I know, they only, they reduce instead of using whole space, they are reducing like 100. As far as I remember, they reduced the whole permutation space to 100. And they actually use some permutation list. So, and then make some index for this permutation. And at the end of the network, they actually estimate 100 dimensional vector that indicate the permutation index, okay? Because there are 9 factorial possibility when we permutate the 9 image patches. They are so many. It's too much to train the network, so they reduce the possibility towards only 100 cases, making this kind of permutation list. And they define they only remain some of the useful permutation cases, and define some permutation index for that and train the network using that. Okay. So so this is too hard to train all the cases. So to make the network to be better trained, they reduce the space. And another self-supervision signal observed by the computer vision researchers are estimating the rotations. Okay, so this was published in ICLR 918, and actually this is very simple. This network is called as rotation network, but they are saying actually they are better than actually previous algorithms like context jigsaw puzzling. That's this one, and this one is context prediction, and that's actually the first. Okay, so they are saying their scheme is simple but better than previous self-supervision signals. What they does is, from the original image, they rotate the images, and what network received as the supervisionary signal was to estimate how much they are rotated. So given this image, the network have to estimate how much they are rotated. Okay, and this paper is saying this is simple, but it is actually better than understanding the images compared to previous algorithms. Okay, and also so far we learned about the self-supervised signals for the image domain, but this is the example for the video domain. Okay, so so especially for the visual tracking, the images from the videos, we have to track some humans or some objects through the video. That's the video tracking application. And for doing this kind of downstream tasks, this paper is involving the self-supervision method like this. So what they does is they involve some convolutional network here and actually learn rankings between for measuring the similarity between the patches. So if these patches are from the same video, their actually similarity or the distance have to be less than the similarity between these and some patches from other video. Okay, so using this as the supervisionary signal, they train this convolutional network. So they actually they does was sampling 3 patches And 2 patches are from the same video, and 1 patch that have to be from the other video. Okay, so these 2 are from the same video, and this patch is from the other video. So first frame, last frame, and this is from the random frame. Okay, so and making this kind of similarity supervision, they train the CNNs. And this is the example for video self-supervision. And also this kind of approaches are also used. So from the original video, this is the sequence, the frame sequence, okay? And we can make the new video having the correct order, okay? And we can make the video by composing different ordered frames like this. So this is the temporarily incorrect video, okay? So using these positive tuples and negative tuples, we can train the network without any labels, okay? This is another example for self-supervisory signal for videos. So what they does is, they have the video encoder. This is the same video encoder, and having some multiple convolutional layers here. And actually they have fully connected layers and to estimate something, okay? So given 3 videos, they have to make 2 videos in the correct order and 1 video as the incorrect temporal order. And the thing they estimate at the last of the layer is which among these 3 videos, which one was incorrect order. Which one is incorrect video? They estimate that index, okay? So somehow they frame this problem as the video classification task and run the network without any labels, okay? And this is another thing, okay? And we will continue from maybe next Monday, okay? Okay, so let's finish here for today. Okay, thank you.